chapter 9. I think there's 4 sections in it altogether. Pretty sure there is. And we're going to be doing today number 9.1, which is the introduction to differential equations. Now, if you do, I'll leave this here for those who want to copy notes, but if you do, is that where you go? If you do a lot of math, especially if you do engineering, you're going to do a lot of differential equations. In fact, differential equations is a branch of math that essentially deals with modelling, trying to find formula that describes some situation, that allows you to make predictions and calculations on it. And it's so important that within community colleges, at least, it goes further if you go to university, we have 2 separate classes called Diff-Ec 1 and Diff-Ec 2. Differential equations 1 and differential equations 2. So for just one topic, there are 2 full classes. So you can imagine how massively important this is, at least for those of you who are going to go on and do engineering. And for sure the sciences as well, you know, chemistry and physics. Less so if you're going to do some kind of, if you're going into the medical field, you won't need differential equations. Don't think you'd need it if you go into computing science. That's probably another branch that doesn't really use it. Okay, so here are the details. You know this eventually will be online, so if you don't like copying, you can always take a picture. Some people do that, or you can just wait till the video goes. Let's talk you through it. Since this is a brand new topic, a brand new subject even within its own right, there's a lot of jargon and structure to it that we kind of have to get familiar with. So a differential equation, everybody calls them DEs or diff-X, is an equation that contains a derivative. Duh, that's pretty easy. Here are some examples of differential equations. Y dash, the first derivative, is 5xy. The second derivative plus 2 times the first derivative plus 1 is equal to x. dy by dx, which is just another notation for y dashed, plus a sign equals x. And the second derivative plus a first derivative is equal 0. These are all examples of differential equations. When you get, hopefully you will take these classes, you'll find that we even have names for different kinds of differential equations. Just off the top of my head, this guy here is called a first order differential equation, and this guy here is a second order differential equation. A first order means that the derivative is a first derivative. That's the biggest derivative you've got. A second order would mean it's got a second derivative in it. So for instance, this one here is a second order differential equation. This one here is a first order differential equation. And within first order differential equations, there are little subgroups. We're, for instance, for the most part, we're only going to do a deal with first order differential equations, right? Ones that only have one derivative in them. And they have subgroups. One is called a variable separable differential equation, which is one of the sections that we'll do in chapter 9. And the other is called a linear differential equation. Now, the reason they have names for them is that if you know it is a linear differential equation, then there's a technique that you would use to solve just those kind of equations. If you know it's a variable separable, there's a totally different technique that you would use to solve them. So one of the tricks of the trade is to look at a first order differential equation and realize what it is. Now, I've done these so much in my life, I know what they are. And this one here, for instance, is a variable separable. And this one here is a linear. And the techniques that you'll discover over the next week or two, and we'll show you how to solve those. So what do you do with the differential equation? You solve it, like you solve all equations. Now, when you solve equations in algebra, you tend to solve them by saying x equals 4, y equals 2, right? You tend to put numerical values. But when you solve a differential equation, what you are solving is you're trying to find out what the function y is, right? Y is f of x. You try to find out if y is x cubed, or is it x sine x, or is it e to the x plus 42, right? So the solution to a differential equation is actually a function of x, right? So it's not 42, it's a function of x. And when we solve differential equations, we end up getting two types of solutions. One is called a general solution, and the other is called a particular solution. For example, if you take this first order differential equation, its general solution looks like this. And it's got a little plus c at the end. So if you ever have a plus c, plus d, an unknown constant, we call that the general solution. This is one example of a particular solution. So it's the same solution, but the difference is that we'll tell you, or we'll find out at least, what the missing c is. In this case, it was 7. So you have differential equations, you solve them, you find a function of x that works, and that solution might have a plus c in it, or a cx in it, or a de in it, or whatever it's got in it. And when it's got those, we call them general solutions. But when everything is known exactly, so there's nothing unknown anymore, then we call that a particular solution to the differential equation. Now, do you go about, in general, solving differential equations? Well, you typically do it by finding a general solution called JS first. They'll then give you some extra information. They might tell you, for instance, the value of the function at 0 is 10, or the first derivative at 1 is 90. And you can use that information to generate a particular solution. This extra information, you know, like this guy here, it's called, depends on the textbook, it's called an initial condition, or it's sometimes called a boundary condition. So that's the big picture. What is a differential equation and the jargon associated with that? I know it's a lot to write, so I'll give you a few moments. Just going to stop sharing for a second in case anybody's came in late. Okay, we're only 2 people short. That's not too bad. So I'm going to have to move on. So if you haven't copied all of this, you know it's going to be in the video layer, right? So you can go back and do it. So what kind of things are we going to do in 9.1? Well, one of the things we're going to do is we're going to check. I don't like that. Check that a given function is a solution to a differential equation. It's a pretty big kind of question. I'll give you an example. This is question 1. We're being asked to show that y equals, a little bit ugly, 7/8 e to the x plus e to the negative 7x is a solution to the differential equation y dashed plus 7y equals 7e to the x. Okay, it's the first time you've seen, I'm assuming, it's the first time you've seen a differential equation before. How do you think we might approach this problem of showing that this guy here is a solution to that differential equation? Any suggestions of how that might be proved? You'll have to hit your spacebar if you're talking, Ian.
Yeah, just solve for one side.
Oh, you mean try and solve the equation? Right, kick this over here and solve it?
No.
No.
Well, I guess kind of. I guess try and make one side of the first equation match the other side of the other side of the second equation.
I'll try to make this look like that.
Yeah, kind of.
If you try to do that, you know you're going to have a derivative over here, and you won't be able to really. It won't be able to be done. It's a good idea.
That one. I forgot what the technique was, but
Last chance.
Can you just plug in y for y and then take the derivative and plug it in for y prime?
That's it. So simply, I won't say simply, but what we're going to do is we're going to find the derivative and plug it in here. We're going to take this guy and plug it in here, and we're going to show that whole thing equals that. And the typical way of doing that is that you set up the left-hand side. And let's see what that is. Well, the left-hand side is this guy plus that. Now, the derivative of this guy, let's see what it is. If you differentiate this fella, you get 7/8 e to the x. And if you differentiate this fella, you get -7 e to the -7x. So far, so good. And then you add I'll check that question. Okay, and then you add 7 lots of this guy, which I didn't plan ahead, so I'm going to have to squeeze it in. Let's see what that looks like. You got this guy, take away this guy, add 7 lots of this. Okay, 7 lots of this guy are 49/8. And 7 lots of this guy is that. That's why I was wondering, my brain, how this was going to work out. Do you see those two guys kill each other off? Now, if you take this fella and you add it to this guy, you actually do get a nice answer. You get 56/8 e to the x. Wait a minute, isn't that just 7 e to the x? And that is what the right-hand side says. So you take the left-hand side and figure out what you get. And when you simplify it down to the end, as long as it equals the right-hand side, you've shown what you need. As a strategy, does that seem reasonable, logical? If I give you a differential equation and I say, prove that this is a solution. Are we good? I have no questions, so try another one then. Oh, by the way, this is only one of many solutions to this differential equation. Yeah, that makes differential equations a little bit nasty, if that's the right word. You know, when you solve a normal algebraic equation, there's a finite number of answers, right? X is 2, or X is 2, or X is 4, right? And that's kind of the world. In differential equations, there theoretically at least could be an infinite number of solutions, right? An infinite number of functions that will work. So it's a little bit less specific. Okay. How about this one? Excuse me for a second. Since I'm making this question up, I'm going to have to make sure it works. Okay. So my second example. There are so few examples of these, I don't want to use what's left in the homework, or you won't get an example that you haven't seen before. So we're going to do here is our differential equation. We're going to be asked to prove that y equals e to the negative x plus 3 times e to negative 3x is a solution. And I'll cover myself by proving or asking, is it a solution? So here it goes. The left-hand side is all this. So it's the second derivative, 4 times the first, 3 times the y. And everything works out right, shouldn't it be equal to the right-hand side, which is 0. A little bit harder to do this, so I'm going to set out the working first. First derivative gets you that. Second derivative gets me that. So if I take 1 of the second derivatives, 2 of the first, and 3 of the original function, which is what my left-hand side is equal to, I get this guy. Plus 4 times this guy. Plus 3 times, I guess I'll put it here, 3 times the original guy, and that's this one. Let's see how that works out. I'm going to have this fella, 4 of these, plus 3 of these, plus 9 of these. Well, if you take this guy, and this guy, don't they all kill each other off? And if you take this guy, and this guy, don't they also kill each other off? So the answer is 0, which is exactly what it needs to be, the right-hand side. If you were curious how I made that question and what I was doing, and that scribble at the side just getting organized, you do not need to know this for this class, but you will if you go into differential equations. This is actually a second order homogeneous differential equation, and it can be solved using what's called a characteristic equation, which is what all that funny R stuff was. So we are done. So if I give you a differential equation and I say, prove to me that y equals insert function here, and do you feel comfortable about the process of doing it? You just take the left-hand side and find out what everything's equal to, combine them together, and it should equal the right-hand side. So in this case, you take all of this stuff and you prove it's 0. There's all the bits that are put together. Here's the left-hand side. Here are its 3 pieces. This is what you got, but the whole thing cancels down to a 0, and 0 is the right-hand side. Do we have any questions? Are you still with me?
So is it basically the same as just substitution?
It is. It's substitution of derivatives. So you substitute a y dashed and a y double dashed for whatever we tell you it's equal to. And we won't tell you what y dashed and y double dashed is. In these questions, don't we just tell you what y is and you figure out the other two? But it's still substitution. For our next situation, we are going to look at questions where you're given a differential equation and you're being asked something a little bit strange. For what values of k does y equal the cosine of kt, say kx, I guess. Then so here's a differential equation. For what value of k will this guy be a solution? So I'm assuming that there are certain values of k that it works and other values of k that don't work. And our job is to find what value or values of k does this satisfy. Well, I'm going to start with cosine of kt. Now, since I know that this will be a solution, I'm not testing is it solution. What I'm testing is what k needs to be for it to be a solution. So I need to find the first derivative in order to get the second. So if you differentiate the cosine of kt and think of t as a variable here, you're going to get negative the sine of kt. Anything else?
Times k.
Yeah. And now when we do the second derivative, we're going to get a negative k squared cosine of kt. Are you happy about where the k squared is coming from and where the sine has now turned into a cosine? Now, these are the building blocks that are going to get used in every second order differential equation. So over here, we have 81 second derivatives should be negative 48 times the original function. So that's going to be 81 of this thing. Is going to be negative 48 of this thing. So I have negative 81 k squareds of cosine kt is negative 48 cosines of kt. Now remember, the goal here is to find out what values of k is this true for. So time to do some algebra. Yeah. Any suggestions for what I should do next to try and get this closer to where it needs to be?
Divide by cosine?
Okay, that's something I typically wouldn't advise, but in this case, I think it's a good idea. We'll assume that the cosine of kt is not 0. Otherwise, that would be a bad idea. Okay. Take me somewhere else. Do something else.
Divide by negative 48. Negative 81, sorry.
Yeah, I kind of knew what you meant. That makes everything positive, doesn't it? Take me a bit further. We're pretty darn close to the end, aren't we here? What you got for me?
Square root.
Right. Oh, darn it. I almost caught myself out here. That is 99% right, but it's not 100% right.
Plus or minus?
Plus minus.
Yeah, almost missed it. So it's going to be plus or minus. You know, you can simplify that, and you should. The first step would be to separate it into 2 square roots, but I happen to know the square root of A1 is 9, so I'll just write 9 down. Can 48 be simplified inside a square root? 16 times 3, which becomes 4 root 3. So there's your solutions. Negative 4 root 3 over 9, positive 4 root 3 over 9. I think the homework asks you to do it in a box and you write it down separately and you put a comma between them. So it'll be something like a comma separated list. I think that's the phrase they tend to use, isn't it? So you write down just what the two things are. And we have now solved this puzzle. So if long as k is this number or that number, this will be a solution to that differential equation. We good? This isn't really a question that they're asking, but I like it. Do you know if I changed it to 3 cosines instead of just a single cosine? Do you know that would work? And it would be the same values of k. If you take a function and you just multiply it by a constant, very often you do not alter the differential equation. In other words, it will work as a solution very often. So it's an interesting property. Which is why there tends to be an infinite number of solutions to differential equations. I'm going to show you the next group of questions because they are kind of, well, it's easier to see them than to write it down, I guess that's what I'm trying to say. I'm just making all these other things go away. While I'm doing this, you want to say hi, everybody, so you can get attendance? There's somebody missing or somebody's not saying hi, because I know there's more than 15 of you here. So who hasn't said hi yet? Okay, that was good. Somebody just kicked in me a hi, but there's 4, 8, 12, 16, 17, 19. There's somebody still not said hi. Jocelyn, have you said hi? Jocelyn, can you hear me? She is good, and she has said here, so she's good to go then. Okay, let's show you what this thing looks like. Right, hopefully you're looking at question 4 from the homework. Now, what you have here is really situation 1 again, but it's kind of done in a different way. There is a differential equation, make it a little bit bigger. Right, you see this guy here? That's your differential equation. And what you have here are functions that might or might not be a solution to the differential equation. So it looks like basically what you do is you take each one and you check it. So you take that one, right, and you find its second derivative. There we go. And then you add the original, which means you add that. And if you get 5 sine x, then that is a solution and you check the box. What you might think is, once I found the answer, I don't need to do anymore. But unfortunately, this question has a lot more work than that, because that one might also work. In fact, all of them might work, or 2 of them, or any combination you like, except probably 0. So you will have to check each one in turn to decide the right answer. And all you need to do is miss one, and it'll keep telling you that you're wrong, and you'll get frustrated. Now, if I can scroll down here. In question 10, same idea, but with a trig function. Question 11, same idea, but with, I don't know, what, negative powers and things floating about. Let's pick one. Right, I'm on question 10. So while you're thinking about it, I'm writing down what the differential equation is. And there are 5 choices there. Do you see them? 1, 2, 3, 4, 5, right? Which one of those do you want me to check? Number 1, 2, 3, 4, or 5? Come on, pick something. You know you want to. Come on, pick one.
4.
4 gets the job. So we are going to check out that guy. And if he works, that's great. And if he doesn't work, then that's also great, right? Because that can be a solution just like things working are solutions. And what makes this just a tiny bit different is, do you see this little fellow up here? So here is my differential equation. And here is the one I'm going to check it against, and then I'll worry about this later. I guess I need to find the derivative. So differentiate this guy, you get 4 cosine x's. And if you differentiate in cosine, you get a negative sign. So that's plus 5 sine x. Okay. So the left-hand side is going to be y dashed, which is this stuff, plus a tangent, of this fella. Now, if life is nice, I guess, shouldn't this horrible mess equal 4 cos squared? And if it does, that's a good thing, right? That means it's probably a solution. And if it doesn't equal cos squared, right, or 4 cos squared, it's not a solution, and we'll leave that one blank, right? It's okay to leave it blank. So let's see what I'm going to have to do here. Well, there's not an awful lot I can do to 4 cosine and 5 sine. Yeah, any idea what the heck I'm going to do with this?
Turn tan into sine over cosine and then distribute.
That's exactly what I'm going to do. Does that seem sensible? Now, the reason I know to go that way is, isn't the right-hand side got coses and cos squares in it? It doesn't have anything with tans, right? So I'm pretty sure that the tangent can't be left as a tangent, right? It's not going to be any good if I did that. So let's see what we now get. Can't really do anything with these two guys again. That times that gets me 4 sine squared x over cosine x. And that times that gets me negative 5 sine x. Well, I'm pretty sure I can cancel that guy with that guy. And so what I'm left with right now is 4 cosine x's plus 4 sine squared x over cosine x. Do you agree I should at least try and simplify this as much as possible, just in case it ends up being this guy? I mean, right now, I don't give it much hope, but I should at least try, right? Now, if you've got a guy that's not a fraction and you want to add it to a guy that is a fraction, don't they have to share a common denominator? So what I'm going to do with this guy is multiply him by a cosine x over cosine x. And that makes this fella that guy. So far, so good. Right, let's make this keep going until we can go no further. If you combine them into a single fraction then, and you pull out a common factor of 4, you end up with that. You agree? Anything nice about this?
It equals 1.
Okay, so what we ended up with is 4 over cosine x, which is really nice, but it's not that. So this is not a solution, right? What you get is not 4 cos squared. That's what you should get if it was a solution. So you don't pick that one, right? And then basically you start at number 1 and you keep going through. And each one that works, you put a dot on, and each one that doesn't work, you leave it blank. I really do want to see one working here, but I'm not sure if I have time. Okay, let's go for it. I'm going to go back, and you're going to pick another one, and you're going to pick one that works now, right? 1, 2, 3, or 4. Oh, I'm not picking 4. I'm not picking 5 either. So 1, 2, or 3. Which one do you want?
3.
Okay. So I have y dashed plus tan xy equals 4 cos squared x. You'll see this in a second. And it is y equals, oh, wait a minute. I've got a nasty feeling about this one. Let me just find out which one it is. I'll cheat. I'm glad I did. I'm picking the first one now. If we had chosen number 3, it would have been interesting, but it would not have worked. So I'm picking one that does work. Just so I can show you an example of one where it is a solution. There we go. Okay, so that's why we got them. This is the derivative. Right, that's going to be a product rule with an f and a g. And that guy at the end is going to get me plus 5 sine x. Because you differentiate a cosine, you get a negative sign. So that's that guy. So f dash g plus f of g dashed with that guy tagged on. So you're going to get 4 cosine x's times a cosine x plus a 4 sine x times a negative sine x plus 5 sine x. So it's going to be 4 cos squared x, take away 4 sine squared x, and that's y dashed for you. So we're now going to take this fella, put a little bracket around him, make it a little bit more obvious who it is. And I'm going to hopefully prove he's that guy. Y dashed and this guy. So y dashed is this horrible mess. So that's 4 cos squared x, take away 4 sine squared x, plus 5 sine x's. Add tan x, which I'm going to replace by sine over cosine. Y, which is going to be this horrible mess. So I'll be writing here all day with this thing. That guy times that guy cancels out a cosine, so you're left with 4 sine squareds. That guy times that guy, the cosines cancel out and you're left with negative 5 sine x. And this guy gets killed off by this one. This guy gets killed off by this one. Yeah, it did work. So do you see what a solution gives you is the same as the right-hand side? In this case, the one we did before, it wasn't the same side. That's why this is not a solution and why this is. We